Hello everyone, this is Ahmed Imtiaz. I'm currently a PhD candidate at Knight Foundation School of Computing and Information Sciences at Florida International University. Uh, Today I'm going to present our paper titled Distributed Network Optimization for Secure Operation of Interdependent Complex Network. So let's look at the outline of this presentation. So first of all, I will discuss the problem statement of this paper. Then I will discuss our methodology that we used. I will briefly overview the proposed two-stage distributed algorithm that we applied in this paper. Then we will show our simulation results that we got. And finally, I will conclude our paper. So let us consider a network that consists of n nodes and an undirected graph G that represents the structure of this network. So in the underlying network, the set of nodes actually represent the decision-making entities. For instance, it could represent a transportation network operator. So we assume that each node can increase or reduce the network flow of the connected lines, such that each node can be either customer or generator of network flow. For example, each node in transportation network can be a parking lot that can help reducing the traffic by housing a number of vehicles, or can increase the traffic by having cars leaving the parking lot and contributing to traffic in the connected roads. So the generic optimization problem formulation for optimal network flow on graph G referred to as OPG, which is given in equation 1. So in equation 1, actually FG represents the physics-based objective function, which depends on the operating cost of the network, as well as the utility function for the network demand. So that this generic problem formulation provides a general structure for the optimization problem to find the optimal operating point of the corresponding network. So depending on the specific application, the objective function as well as the constraints will be formulated to reflect the real world limitations. So decision variables here are represented by xg, and functions gg and hg actually denote the corresponding inequality and equality constraints respectively. So Lagrange multipliers are corresponding to inequality and equality constraints and are represented by mu g and lambda g respectively. So in order to develop an efficient distributed algorithm to find the network flows and pave the way for secure operation of interdependent complex network, so we propose to develop a two-stage solution. So in the first step, we leverage array steps Frankel's algorithm to deal with the nonlinearity of the objective function, such that the fg in the objective function. And we would like to transform the problem into a sequentially linear optimization. So in the second stage, we propose to use a distributed linear optimization algorithm to solve the linearized problem. So first, we consider array steps Frankel's algorithm, and this Frankel's algorithm actually transforms the original linear convex problem into a series of optimization problems with linearized objective function, while ensuring that the solution is in the feasible space spanned by the original constraints. So in order to improve the convergence of Frankel's algorithm, we propose to use an enhanced Frankel's algorithm, which is referred to as array steps Frankel's algorithm. So in this algorithm 1, actually this represents the pseudocode of array steps Frankel's algorithm. So similar to the pairwise Frankel's algorithm, it avoids zigzag phenomenon, and it has an improved convergence rate, and it can move faster to the optimal solution. So there are several distributed convex optimization algorithm. For example, the Bender's decomposition, which is applicable in case of having complicating variables. And we also have Dengin-Wolf decomposition, which is applicable in case of having complicating constraints. So these are the two major decomposition methods to solve linear optimization problem in a distributed way. So as we deal with coupling constraints, we use Deng-Wolf decomposition. So Deng-Wolf decomposition algorithm has been widely used to solve a linear optimization problem in a distributed fashion. So specifically, it is applicable to large scale linear programming with block diagonal structures. So in order to solve the sequentially linearized optimization problem using AV-Step's Frank-Wolf algorithm in a decentralized fashion, we can use distributed linear optimization methods. So in this paper, we used Deng-Wolf decomposition to find the Frank-Wolf direction. So to this end, Deng-Wolf decomposition is used to determine the Frank-Wolf direction in line 2 of algorithm. And a detailed implementation of Deng-Wolf decomposition for a generic linear optimization problem is provided in reference 34. So in the proposed bilabel decomposition algorithm, actually, which is the coupling of AV-Step Frank-Wolf and Deng-Wolf decomposition method, the central coordinator or agent only needs to receive the gradient of objective function. So at the linearization point, which is integrated in line 3 of this algorithm. So for the simulation result, first we analyze our distributed method to find optimal operating point of a randomly generated network. We conduct a simulation using multiple networks with different sizes to evaluate scalability. So we assume that each node in the network can be a demand node or sink or a generation node or called source. So if a node does not have any source such that outflow to the network, we choose the value of the source to be 0. Similarly, if a node does not act as a sink such that inflow towards the node, we choose the sink value to be 0. So this can cover a wide range of practical real-world networks such that, for example, energy networks or traffic networks. So we distributed the computation over agents using Deng-Wolf decomposition. It should be noted that this does not mean there is no coordination among agents, as there is still a master problem that receives some information from each agent at each iteration and ensure the convergence towards the optimal solution by sending control signals to each decision-making agent. So we generated a random network as a connected graph for our experimental evaluation, where each vertex indicates a node and an edge represents a connection between two nodes. So the network is constructed by randomly generating coefficients and establishing a non-repetitive connection between two nodes. So we establish a non-repetitive connection by scanning all available node links and creating a new connection that is not present in the network. So in our generated random graph, actually each node represents a path that can be viewed as a subproblem. So our original problem is divided into V subproblems such that a node I represents a subproblem, and we directly solve the flow on each branch. So we consider that each node has a positive and non-zero degree, such that degree greater than 0, and each node is connected with a minimum of one node. So we ensure that by connecting a node to its neighbor and further generating some random connection among the nodes. So in figure 2a, actually we have shown a simple network with 10 nodes where each node has degree greater than 0 and total number of connections is 40. So in similarly, we generated random networks for 50 nodes, 100 nodes, and 500 nodes, which are shown in figure 2b, 2c, and 2d. So here we can see the simulations results considering like 1 to 10 node cluster, 1 to 50 node cluster, 1 to 100 node cluster, and 1 by 500 node cluster. So as we discussed, A-based Frank-Wolf algorithm transforms a nonlinear convex optimization problem into a linear problem. So Frank-Wolf algorithm starts from an initial point, and in every iteration, actually, we observe that we observe that the objective values get reduced, so such that the algorithm converges. So we tested different network nodes to observe their convergence behavior. So we noticed that as network size increases, it takes more iteration rounds to reach convergence. And actually in figure 3, we represent the convergence simulation for different sizes of network, such that network size 10, 50, 100, and 500. We can observe that the smallest network, which has a size of 10, takes the least number of iteration, while the largest network, having network size of 500, takes the maximum number of iteration among all considered networks to reach convergence. So here we represent the computational time for different sizes of networks. So in a conventional approach, the increase in network size significantly increases computation time. Therefore, in a larger scale system, directly solving a problem with the increment of network size may encounter a large or fast growth of computation time that may cause failure in solving the problem due to computational complexity and also memory limitation. So our proposed two-stage method actually tackles this issue by distributing the iterative updates among agents, and rather than solving a centralized problem that includes all decision variables. In this figure, actually, we illustrate the scalability of a solution with increasing the number of nodes. We can note here that adding an additional node increases the number of variable by at least 2, and one generation and one demand variable. It will also affect the network flows if the node is connected to other nodes. So we also compared our proposed approach with centralized optimization approach by considering 33 bus power distribution network having 4 clusters. We solved that with both centralized method and our proposed distribution optimized method for multi-cluster operation, and we obtained less computational time than centralized approach. So in this paper, we focused on formulating and solving a generic network flow optimization problem using a two-stage scalable solution. The main idea is to solve a large-scale decision-making problem in distributed fashion to reduce the computational complexity, ensure scalability, and preserve privacy of intelligent agents. So this requires holistic understanding of the objective function and constraints of the underlying networks and how they can leverage available computational resources to enhance efficient operation of the network. So the proposed algorithm distributes intelligence among heterogeneous agents in a complex network represented by a graph of nodes and edges among them. It first linearizes a convex optimization problem with quadratic objective function, and then solves the linearized problem using a distributed algorithm. So in order to evaluate the distributed algorithm for linear constraint optimization with a quadratic cost function, we used a random network with different number of nodes and edges. We illustrate the runtime and convergence of the distributed method over various network sizes. The detailed convergence evaluation, runtime and scalability analysis of the distributed optimization of our random graph shows the effectiveness of our two-stage solution. So in our future works, we plan to extend the scope of the proposed algorithm and evaluate scenarios that include multiple cluster of nodes rather than having only one network. And given the fundamental nature of the paper, it can be broadly deployed in various real-world decision-making problems, such as optimal operation of critical infrastructures. So this is the references that we used in our paper. And if you have any question, you can contact us through this mail address. Thank you. That's all for my presentation. Thank you.